In this video, I'm going through the Student Success Sample Project. I have already read through the syllabus, so if you haven't already, pause the video and read through. Just from a high level, I can see that the goal is to build a model that is accurate and then to interpret which factors are important. They have already done some preliminary analysis and given us some setup code. The format of this exam is an executive summary, and then data exploration and feature selection, then selecting some models. One will be a decision tree and a random forest and a GLM, and then there'll be a section on findings and recommendations. The middle two sections can be technical. The beginning and the last section are non-technical. And they say there are 29 predictor variables, which is quite a lot. There are 4 variables that are related to the target variable. The goal is going to be to predict whether or not a student passes their final trimester with a grade of at least 10. And they give us some specific questions about data transformations. So here I have the template on the left and I have the Word document on the right. Now I'm going to write this executive summary last because I can't write the executive summary until after I have the results from the other sections. Okay, so I've loaded the data and I can look here at the 29 columns. And unlike the hospital readmissions project, they don't have a list of tasks. So the tasks are basically contained in the project statement and in this RMD file. They give us some code chunks. They tell you how to construct a box plot, and they give you some code in order to convert factor levels to those which have the most categories. And they call the dataset full.ds, which in my opinion is a terrible name because it takes so long to type and it requires capitalization. So I'm going to press Control F and then copy and replace this with just df, which I think of as data frame, which is just very easy to type because the D and F are right next to each other on the keyboard. So now I don't actually read the data because it's already in the R library. So I'm just going to call that student success. And then I can see that there are 585 observations, and this is showing you the values of D3. I like to use count. I have to load the tidyverse library, which will be on the Prometric computer. I want to count the G3 column. Okay, you can see that there are some negative values, and if you look in the project statement, G3 is the grade of the final trimester. There are 4 variables observed. Okay, the grades are on a scale of 0 to 20, but we may want to model just the pass rates. You can figure out a way to build a model for whether someone will pass instead of the overall grade. So there are 3 students that have a grade of less than 0. I removed 3 students who had grades in the final trimester that were less than 0. And I like to start off just by summarizing the data overall. There were 29 predictor variables and 585 observations of students. I'm not going to worry about fixing spelling because I could do this at the end. I'm just going to use the word review grammar and spelling at the very end. So these are related to student demographics and lifestyle. The target variable is whether or not a student passes their final trimester by achieving a grade of at least 10. Just look at the other grade values to see if they're always positive. Yes, G1 and G2 were always 0 or greater. And then they create G3 pass flag. I don't like to use uppercase letters in my column names because it takes longer to type. Better yet, I'm just going to call this pass, and then they remove these other variables. Another way of removing variables is to use select and then minus the variable name. So if I want to if I want to unselect pass, you just use that. Data exploration and cleaning. So I suppose technically you should do all of the exploration and filtering in this RMD section because the grader will expect you to. So I wanted to filter G3 is greater than or equal to 0. And if I look here, I'll see that there are 585, and then there are 582 afterwards. You can look at a summary, and there are 29 predictor variables. It would take me a long time to go through each and every one of them. I believe that's why they gave these questions here, so that you only need to answer the questions that they ask you. The first question we have already answered. The second question, we want to use 29 predictive variables in order to advance, in order to model G3 because we know them before the school year starts. But in the data set we have includes G1, G2, and absences. They have been removed in the RMD file provided. Okay, so in other words, because our goal is to help educators identify which students will pass at the beginning of the year, we only use variables which they would know in advance. We do not include the G1, G2, or, well, school failures would not be known. Other variables. School is fine, sex is fine, age is fine, address, family size, parent status, education status, reason to choose school, guardian, travel time, study time. One could argue that these would not be known in advance because they could change throughout the year. Failures. So we don't know failures of the current school year until the end of the school year. Internet, romance, these other variables, except for absences, and absences would not be known in advance. Okay, I'm just going to go back and read again. Okay, so we have completed tasks 1 and tasks 2. Let's go back and actually remove them. So say df is equal to df and select minus absences, failures, and I cannot spell absences. They've already removed absences. So it seems, yes, they already removed absences. Okay. Even if they are the ones who do something like they are the ones who remove G2 and they removed G1, I still say that I did that because technically it's part of the analysis that I did. This is okay. So the next question is, this is a good time to decide if records with unusual G3 values should be removed. Okay, I've already done that. But because they asked me to put it right here in the RMD file, I'm going to put it right there. It appears that there are some outliers. I've used my boxplot function to look at age versus passing. Possibly should be done for other numeric variables. Okay. Let's look again at the values. Age goes from 15 to 22. That's reasonable. What is the age of these students? So School Whiz is a group dedicated to providing remedial education to troubled students. These are high school students, right? It just says there are 29 predictive variables collected prior to the student entering the formal school year. It's not really clear. We notice that the ages go from 15 through 22. Some of these students are probably too old to be included with the other students. I'm going to just search Control F for age. Okay, they say age is a student's age from 15 to 22. And it does. The data dictionary says that it goes from 15 to 22. They don't give us any other information about the age. This matches the description in the data dictionary. Address, family size. Family size is, so if I have these character variables and I want to see the counts, I can use mutate if is character as factor, and then I can actually do select if. I can just select the characters, and then summary is factor, I suppose. Here we can see all of the levels for the factor variables. I'm using Control left bracket in order to adjust the font size. And let's do this for the numeric variables. Select if is numeric, right? So I'll just create some bullet points. All students came from one of two schools. What is address? It's either R or U, where, no, I believe, so what does address stand for? Address is student's home address, urban or rural, in an urban or rural address. Family size, so GT3 is greater than or equal to 3. Add families of at least 3. Say most had. What is P status? Parent status, apart or together. Most had parents that were together. The most common job was services, was actually other. And most common father's job was also other. What does other stand for? They don't tell us. What is reason? Reason is the reason to choose the school. Most have a mother as their guardian. School support. Most do not have school support, as only 58 students have support. And what is school support? It is extra educational support. Family support. Paid. What is paid? Paid is extra paid classes. Activities. About half of the students participate in after school activities or extra activities. Nursery is attended nursery school. All right, this is taking me a long time. Higher is wants to take higher education. 559 students said that they wanted to take higher education. I'm assuming that's at least college. This would imply that these are high school students. Internet, 98 students do not have internet at home. I find that difficult to believe. What year was this data collected in? This is difficult to believe. Romantic, has a romantic relationship. 225 do not. So about half. What is pass? Pass is, so pass is the target. That's the flag. So 200 students. 201 students passed with a grade in there with a G3 of at least 10, and 381 failed. That seems very high. That seems very high. Let's check. Yeah, that's what it says. So that's a pass rate of 201 over, that's a pass rate of only 35%. Right, half of the students are in a relationship, 34% pass. The average age is 16. MEDU. MEDU is the mother's education from 0 to 4. Okay, so average mothers and fathers education level was 2.85, 84, 5, 2.9, and 2.7. So their mothers are on average more educated than their fathers. Travel time is on average 1.4. Now it's interesting that these are numeric values when they're really referring to minutes. So it's 1 to 15 minutes, 15 to 30 minutes, 30 minutes to 1 hour. So they are in order. And that means that they could be used in a model either as a numeric value or as a factor. If they were out of order, like if let's say 1 referred to 1 hour to 2 hours, and then 2 referred to 1 hour to 15 minutes, or 15 minutes to 1 hour, then they could not be used as numeric. They would have to be used as a factor. But because they're in an increasing order, it will work to use them as a numeric value. Travel time is a numeric value where a higher increment value that is in buckets of less than 15 minutes, 15 to 30 minutes, 30 minutes to 1 hour, 1 hour plus, which means that we can use the numeric levels from 1 to 4 directly in the model. The mean travel time was 1.841, which doesn't have a clear interpretation, but that's okay. It's just a numeric value. Similarly, study time was a numeric value with a mean of 2. Go out with friends. 1 is very low. 5 is very high. So is it better in this case to look at these from a frequency perspective? If we want to do that, we can say df mutate at, well, no, I'll just say select, and then I'll select the variables that I want. So let's say that I want to select travel time, study time, famrel, free time, go out, delk, welk, health. So what I'm doing is just looking at all of the variables that have a numeric range, like travel time, study time, free time, and so forth. I select these, and then I want to mutate all as factor, and then run a summary. I don't think they expect you to be able to do this. However, if you do get a question like this, it cannot hurt. Because some of these variables were numeric with a range where a higher value indicates more of something, such as more time traveling or more alcohol consumed. I converted them as two factors to look at the frequency of each level. I noticed that most students travel less than 15 minutes, study, where's studies time? Study 1 to 2 hours per week, or per day. It must be per day. What is family relations? Family relations, quality of family relationships. Very bad is 1. Have family relation status of 4 out of 5. Free time is, it doesn't say, it just says 1 is very low. Free time is 1 is very low. Have of 3 out of 5. Go out, whatever 3 out of 5 means. Go out with friends, 3 out of 5. I don't know how, see, the interpretation here is really vague. 3 out of 5. Maybe this means like 3 out of 5 days per week. I don't know. DELC is weekday alcohol consumption. 1 is very low, 5 is very high. Do not consume alcohol on the weekdays often. WELC consume alcohol most often on the weekends. Health status is mostly a 5. This is the current health status. Are in very good health. Okay, and it appears there's some outliers. I've used my box plot function to look at age versus passing. So these are the failures. And you can see that they have a higher age on average. So put this into the graph. It's hard to know what exactly they're looking for. And so I just include anything that I think they might want to see. Students who fail are older. Let's just look at the age. So let's get the average. Let's get the percent of let's get the average age by those who pass versus fail, and that is 16.9 versus 16.5. Okay, for categorical variables, which for this purpose could include those on 1 to 5 scale types, I find a way to make bar charts. Oh, great. We've already spent a lot of time doing this. Mother's education versus pass and failure. Oh, okay. We haven't looked at this graph yet. MEDU is odd. Would expect more passing with more mother's education. Not clear what 0 means. Can someone really have no education? No time to check with my bosses here. Few in this category. Only 3 have no education. So I'm just going to remove those. DF filter MEDU is greater than 0. I noticed that there were 3 students whose mother's education was listed as 0 because this did not make sense given the data. Because this did not make sense, I removed them. Let's look at the father's education. There were also 2 students with FEDU of 0, which I removed. So this says 4 categorical variables, which for this purpose could include those on 1 to 5 type scales. I found a way to make box plots. So they expect you to do this for the other categorical levels that are on the scales of 1 to 5, which is what we have already looked at here. But it's if they give you something, it's always a good idea to show that you know how to use it. Like, let's look at weekend alcohol consumption. I'm just creating graphs so that I can put stuff in the report. That's basically it. Okay, let's do this for, well, this is weekly. Let's also do this for daily. And this is weekday. Okay, I also looked at some bar graphs to examine, to see how the students, I also looked at some bar graphs. Here's an example that shows that students party on the weekends. Probably not actuarial students if they're in high school. Here's an example. Okay, what else do we have to do? Created some graphs, variable exploration, remove records with questionable values. Consider removing variables that appear to have no predictive power. Okay, I've already done a lot of this stuff, so my solution is just going to be to move my code down into this section because I want the grader to see it and to give me credit for it. Okay, see if there's anything else that they said in here. We wonder if we could create some new variables based on those we have to improve accuracy. For example, we think that parent variables may be important. It might be worth playing around with several combinations. It might be. So when they say it might be, it means that it is. Calculate correlations to numeric variables. So here's a correlation matrix. And let's view this. Okay, so age. So on the diagonal, you can see that the correlation is 1 because each variable is correlated with itself. If we want to, we could throw this into Excel quickly and then better picture. Oh, okay, maybe not. We could write this to a CSV file, core df, write CSV, and okay, I can see that failures is negatively correlated with mother's education. Father's education is also negatively correlated. So as you increase their mother's or father's education, you decrease the number of failures. Do they expect us to include this? We looked at the correlations and noticed that some mothers and fathers' education was negatively correlated with the number of failures, minus 0.25, minus 0.29. And we also see weakened alcohol consumption and mother's and father's education status, see age, and alcohol consumption are positive. Is that older students tend to party harder. Age and positive correlation, which means that older students tend to party more. And mother's education and father's education are correlated very strongly. I wonder why that is. When they say the word feature selection, what they're referring to is how you use the original variables to create new variables, which they call features. I say that because features is often used just to refer to anything that goes into a model, even the original variables. It's just a word. So but when they say features, they mean variables which did not exist originally in the data set which you created. So that, I suppose that's in this next section is called feature creation. So we have mother's education and father's education. It makes sense to take the combined education. So I'll mutate. I will say parent edu equals medu plus fedu. You have any other ideas? Well, what about the ratio of alcohol consumption to, or the ratio of free time to study time? Free time, study time ratio. Or how about travel time plus study time. Now, I don't want to make a linear combination of variables because this will cause issues with linear models. How about failures? Should failures be included? I just realized because failures is the number of past failures, right? The number of past class failures. I suppose it could be included. It's referring to class failures, not the semester failures. So I could say, let's take failures divided by age. Just call this failures age ratio. And maybe their health status and their alcohol consumption, because these are numeric, right? So I'll multiply the two together. So if their health status is bad, if their health status is, let me see that I have this sign, the interpretation right. Current health status, 1 is very good, 1 is very high, okay. So let's do alcohol consumption divided by health status so that it will be highest when this is really, if this is really high, if the numerator is really high and they're in poor health, then this will be very high. Conversely, if they're in great health, it will not make as much of a difference if they're consuming a lot of alcohol. Okay, I think this is enough. I don't think we need to create any more of these features. It's good to just look at the summary of the features that you created to make sure that there are no blank values. So the ratios are between 0 and 1. Health alcohol is between 0 and 10. And because we created a linear combination, parent edu is mother's edu plus father's edu, we have to unselect the original variables, and we also want to unselect G3. Okay, now it's based on these correlations and the results from the earlier work, I created new features to test in the models. These were the combined parent education, the ratio of free time to study time, the ratio of failures to age, and the ratio of total alcohol consumption to health. I removed the MEDU and FEDU columns to avoid having a linear dependency. Okay, next task, prepare data set for modeling. I need to remember to do this only after all the cleaning and feature creation is done. That ensures the training test sets both contain the variables that will be used. Stratified sampling should be used to handle an imbalanced sample, approximately 65% passing and 35% failing. We want to make sure we don't get more passing or failing individuals or trainer test sets. I'm going back to the project statement to see if I've missed anything. So they said the grades are on a scale from 0 to 20. I removed a few students here. We only want to use 29 predictive variables, and I removed absences and what was the other one that I removed? And I removed, where did I talk about this? Because our goal is to help identify which students will pass, only use variables in advance. We do not include G1, G2 failures and absences. Okay, so I do have failures, so I should drop failures. And here I'm getting an error. I'm getting an error because I'm trying to deselect a variable which I've already deselected. The way to fix this is just to run all of the prior chunks. So I'll press run chunks above. I've already unselected this already, and I'm looking for the code where I selected failures. Here it is. So I'm going to remove that, and then, well, let me rephrase that. Because I can't use failures at all, it would be incorrect to even use failures in this variable here. So I'm not going to use this column because I'm not supposed to use information on failures whatsoever. Okay, let's just create another variable. Let's say travel time and address. If their travel time is 2 or greater times their address. This isn't very interpretable. Let's think. Let's use any support. So if they're family support, if they have school support or family support. So this is if else or school support equals yes. All right, now I need to revise what I said. The ratio there or not the student had any support. I'm also going to remove school support just so that there's no linear dependency between the support column and the family support and school support columns. Okay. Now I've created some new features, and I just want to make sure that failures isn't in here. That would be a failure on my part, and it is not. Good. Okay, now I will move on. So I have to change all of these pass flags to the column that I named it, which is just pass. I'm just going to replace those. Okay. In order to ensure that the model will perform well in real life, I used a blind holdout set of students, of 75% of students. The model was trained on the training data and evaluated on the test data. Because the data is imbalanced, there are more students who fail than pass. I used stratified sampling of 65% passing and 35% failing. The pass rates are below. For each data set are below. This is train test. Okay, so you just want the pass rate to be the same in the training and the test set, and it's true that they're about 35%, 65%. The next step is to build models. Build a model to predict pass or fail. The following code runs a decision tree classification model on pass. Using all variables except for G3, it uses the full data set. The control parameter is used to set the min bucket, CP, and maximum depth parameters. Okay, so this is a long section. This one section is model selection and validation. So I need to do a lot of writing and put in a lot of output. The first model that I tested was a decision tree to predict pass or failure. This decision trees are a model that puts each student into a bucket based on a series of yes/no questions. I tested out all variables and tuned the hyperparameters min bucket, CP, max depth. These control the minimum number of students allowed in a terminal node, the complexity parameter, and the height of a tree, respectively. If you don't know it, if you just didn't remember what these were, you could just go to $rpart into the console to find the documentation. And then you would see all of these options. You take it, rpart takes all of these things. One of the arguments is parms, which stands for parameters. Control is a list of options that control the rpart algorithm. See rpart control. And then they give you the list. They give you the min split, min bucket, CP, max complete. So you don't have to remember any of this. You can just look in the documentation. So excluded variables, G3. Now this is strange that they expect that G3 would still be in the data set, but I've already removed it. Okay, so they load rpart and they set the random number generator seed, and they want to take the name. They want to take data and then take all of the names except for those that are excluded. So if you just run this section, oops, well, you know excluded variables is G3, right? So you just say this is equal to G3, and then if you run this section of code, you'll see what they're talking about. Well, this just creates a data frame, and then I can look at the names of that data frame, and it's just every variable except for G3. So I can just get rid of this because I don't have G3 in the data anyways. And then here's my decision tree. The first decision tree that used the default parameters was too complicated. I wanted to make the tree simpler to interpret. Now, how can you do that? Well, you can see CP is a complexity parameter. So when the complexity is high, when the complexity penalty is high, the model will favor a simpler tree. So if I increase this by 10, and the maximum depth is the maximum height of the tree. So this tree is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So this is a height of 10. This is saying you could use a maximum height of 20. Let's just say I want a maximum height to be 5. And the min bucket is the minimum number of observations that are allowed in one of these terminal nodes. So if this number is really small, then it means that you could just be overfitting to, like, there could be 5 observations in this bucket and 5 observations in that bucket. If you increase this number to, let's say, 20, 50, it means that the tree will have fewer end branches. And now if you look at the tree, you'll see that it's very simple. So let's use, this is maybe a little bit too simple. So let's relax these assumptions a little bit. Let's say min bucket is maybe 30. Okay, this looks right. Now, this is not how you fit a model if you want to get high performance. This is actually a very bad way to get high performance because it's likely that you are just creating a model which already reinforces what you were thinking. It's not really statistical, it's not scientific. If you wanted a model that had high performance, you would use cross-validation to test out hundreds of combinations of these parameters and then choose the model which gave you the best performance on a holdout data set. But this is just an exercise in creating a decision tree that is interpretable that I can put into the report. And so I'm just manipulating the parameters to do that. Not sure why this isn't working. There it is. Export. Copy to clipboard. Let's make this a little bit smaller. Oh well. I lowered the max depth of the tree to 8, increased the complexity, where a higher value means that complexity is more penalized, and increased the min obs per node to 30, which is the minimum number of patients allowed in a terminal. A higher value indicates a simpler tree. Now they have you look at the cutoff and the predicted value and so forth. I want to go back to the default. I think that I forget what this was at originally. So I'm going to go back to the original file so that I can see what the parameters were, because I want to recreate them. So these were min bucket, max depth. Okay, so this is their tree, the really, really deep tree. And then what I want to see is just the cutoff, is the confusion matrix. So here's the default. And here's after adjusting, after tuning. So this accuracy is 84%. But the accuracy is not that useful because you know that overall only 34% of students pass. And so this is saying 144. It's easier if you look at these in terms of a percentage. Well, how many rows are there in train? There are. I'm confused. Train the so this is giving you train the decision tree on the whole data set, which would be really bad because it would result in overfitting. So you only want to train the model on the training data. Okay, so this should be train, and then predict should be on predict test, and I want to predict DT new data. This should be test. Okay, so let's go back and update this. Say our accuracy was 69%. Say was 69%. However, because we have imbalanced data, accuracy is a unreliable metric. It will not show a model that predicts more students failing rather than passing as being better, but will show a model that predicts mostly passes because this is the majority class. So the accuracy was 69%. The sensitivity was 58%. This was the percentage of passes of students who actually passed that did. So if you take 29, the students who were predicted to pass. So you take 23. Well, so the total students who passed, passers, was 23 plus 71. And the predicted passes were 21. So if you take 21 over passers, you get 22%. If you take, and I just typed in question mark confusion matrix, and it brought up all of these useful formulas. So if you have a matrix like this, so this is predicted reference. So sensitivity is A over A plus C. So that's in that case, the number of failures over the number of failures over the total failures. So it's the probability of, it's the ratio of the model's predicted failures to total failures. The specificity, D over B plus D, so that's D over B plus D. That's the ratio of students predicted to pass. It's the ratio of predicted students to total students who passed. So if I look here, specificity is 75%. So if I take D, which is 71, divided by B, which is 23 plus 71, I get 75%. And the specificity here is 75%. So the specificity is the percentage of students who actually pass that are predicted pass. This is 71 over 23 plus 71, or 75%. Now, is this, in this context, do you think SchoolWiz cares more about predicting which students will pass or which students will fail? I think in this context, they're trying to help to improve students who are about to fail. They want to tell professors or tell teachers quickly so that they can take measures in order to help those students early on in the semester before it's too late. So I think in this case, looking at sensitivity would be better. Sensitivity, again, is the ratio of predicted failures to actual failures. A over A plus C. So A is the true negatives. I always get these mixed up. I believe this is true negatives over A plus C, which is the total failures. So it's the ratio of students who are predicted to fail who actually failed divided by the total failures. So let's just check. 29 over 29 plus 21 is 58%. The sensitivity is the percentage of students who fail that were predicted to fail. SchoolWiz cares about helping students early on in the school year before they fail, before it's too late for them to recover their grades. And so sensitivity is a better metric to look at than accuracy. This is 29 over 29 plus 21, or 58%. This is, I think, perhaps a little bit more detail than they're looking for. However, if they asked you to calculate these things specifically, or if there was another question on the exam which dealt with these classification metrics, it's useful to know how to get there. So to just look at question mark confusion matrix, and you'll get all of the definitions that you need. Okay, now remember, this was the baseline model, right? However, we had another model. We can look at this one and see the accuracy is higher, 72%. The sensitivity is actually a little bit lower, 55%. The specificity is higher. So if you have higher accuracy and you just want to adjust the sensitivity or specificity, that means you should change the cutoff. You can also look at the kappa value. Kappa here is 32. So for kappa, it's between 0 and 1. Higher is better. So here kappa is 33. Here kappa is 37, which is better. So if I try changing this cutoff value, I can keep the model parameters the same, but my sensitivity will change. So here it's 66%. Let's say we set this even lower. We can get the sensitivity up to 78%, okay? So again, the accuracy is 64%, but accuracy is not that important here. Yeah, I think this is a good start. I chose which gave a high sensitivity so that School Whiz will be able to help those students who are likely to fail. The sensitivity is now 78%. The accuracy is 65%. But again, because this data is imbalanced, this is not important. Specificity is 57%, 58%, 58%. What was it before? 76%, which is lower. I don't even need to mention that. I'm just talking about sensitivity. Okay, I don't like the way this looks, but I don't really. The grader doesn't, as long as it's readable, it doesn't need to look perfect. Okay, the tree below shows that, insert a page break. So here the color represents the pass rate. So green is a high pass rate, blue is a low pass rate. So these green students here have the highest pass rate. So if students have with no parent education, parent EDU is not equal. I can't actually I can't tell what this is saying. Is this parent EDU is less than something, right? Parent EDU is less than 5. Parents with education, so if they have, so 5 is probably the number of years of education, where a higher value is better. Parent EDU, mother's education. So students with parents who have at least a college degree, 4 years of education, and who go out at least greater than 4, and who go out frequently, have the highest pass rate of 45%. Students with parents, so I just went down from here to here to here. Now I'm going to go from here to here to here. So parents who have at least a college degree, who do not go out very frequently. Let me rephrase this. So right is no, left is yes. So if they go out very frequently, right is no. So these are students who do not go out very frequently, and who do not. So because this is saying, is go out greater than or equal to 4? No, because I went right. Students who with parents who have at least a college degree, who do go out very frequently, so that I went left, which is yes, and who had health alcohol greater than less than 1.7, who had a health alcohol of less than 1.7. Now remember, this is the ratio of alcohol to health status. So a higher value means that the student is less healthy. They're living a less healthy lifestyle. So when this is not less than 1.7, it means it's greater than 1.7. Greater than 1.7, their pass rate is 7%. I believe I'm misreading this. I am. So the pass rate is this middle number. You can see these are in order. 36, 62. Wait, no, they're not in order. The percentage is the percentage of observations. See, it starts out here at 100%, meaning that 100% of the observations are in this top node, and then it splits 35 and 65%, and then 20%. So the pass rate is actually the middle number. So this top is 83%. And then this node is 74%, and then less than 1.7 is 45%, and then so now we finished all of these nodes, and we have to go down these paths. So students with a parent's education of less than 5 years who had a mother that was not a health or a other of 16%. And finally, done. Let's move on to the next task. Random forest classification. The following code runs a random forest classification model on pass. Using all variables except G3, it uses the full data set. The code runs through the repeated cross-validation and produces the best fit model based on accuracy metric. After the model code, there are some diagnostic outputs such as the variable importance plot and confusion matrix. Okay, so again, this is the excluded variables, which I've already removed. The data here is using DF. Now, in a perfect world, if this was a real modeling scenario, you would be using cross-validation based on the training data. You would then select the hyperparameters, which have the best cross-validation results. Then, if you wanted to compare models, like let's say you wanted to compare the random forest to the decision tree to the GLM, you would then evaluate all three models on the test data. And in this case, because they've already seen the test data, because the model here is using the combined data, even if it's into cross-validation, it's still going to be overfitting slightly. But this is just the way that they've set it up. So I'm not going to change that because they were the ones who designed this. And this is using train control. Method is repeated cross-validation. They run cross-validation 5 times, which means that they divide the data set into 5 groups, and they use the first group as the holdout set and the remaining 4 groups as the training data, and then they do that again, where the second group is the test set and the other groups are the training data, and they do this again for each of the 5 groups. And then finally they take an average of the model error over each of those 5 buckets. Repeats equals 2 means that you then repeat that entire procedure twice. Okay, so we just have to, so a random forest is an ensemble method which bags decision trees. I used the final prediction is an average over many decision trees, which improves the, which makes it more difficult for the model to overfit and reduces the variance of the predictions. I used cross-validation with I used 5-fold cross-validation with 2 repeats in order to tune the parameters mtry. What is mtry? That's a good question. Let's look in the random forest documentation. mtry. Number of variables randomly sampled as candidates at each split, which is, that did not work as I expected, which is the number of variables sampled at each split, as well as entry. Entry is the number of trees. Yeah, now it's more difficult to overfit the number of trees because it is difficult to overfit It is difficult to use too many trees to set n-tree too high because the model is taking an average. If you increase n-tree to say like 10,000, then the trees on average do not change, right? Each tree still has the same height approximately, and it's still using the same number of variables. And so you just take an average of like 10,000 trees, and it's still an okay estimate, which means that when you tune, so this just means that we use a value of 500 for n-tree and only tune mtry using cross-validation. It is technically possible to use too many trees. It's difficult to do though. So in this case, what they're doing is reasonable. They're just tuning mtry using the grid, and they're just setting n-tree to something high. I noticed that the default was 50, but this is low, and so I increased it to 500. And mtry, they're testing from 15 to 25. If you look at mtry, the default is the square root of p, where p is the number of variables. So if you look at ncall of train, you'll see that there are 30 variables. So if you take the square root of 30, it's about 5.4, right? Where here they're considered, so this is just a rule of thumb, which is to try something close to the square root of p. Now this says for classification, you use the square root of p. For regression, you use p out of 3. In this case, we're using classification because we're predicting a pass or not pass, right? So I'm going to lower these. I'm going to start with 5. I'll start with 4, and I'll go 5, 6, 7, 8, 9, 10, and then let's just see. And it goes without saying that the more parameters that you test, the longer it will take for R to run, because it has to fit a model for each of the combinations that you have. So maybe this is too many. This is still running, so I'm going to just do 4, 8, and 10. Because how many models does it have to fit, right? It has to fit one with mtry 4, one with mtry 8, one with mtry 10, and it uses cross-validation 5 times, and it repeats it twice. So it uses 3 models times 5, which is 15, times 2, which is 30. So it's fitting 30 different random forests. And each random forest has 500 trees, so that's 30 times 500, so it's 15,000 trees. 15,000 decision trees. And if I was at Prometric right now, I would decrease this. Okay, it looks like it finished. And if you just run plot, it will show you number of randomly selected predictors, which is mtry, against accuracy. Here is the result. So it looks like accuracy is highest when you use a lot of trees. The accuracy is highest when using mtry equals 10. And this sets the cutoff of 0.5, but we already found that using a lower cutoff is a little bit better. Oh, I should mention this. Did I include the fact I also decreased the cutoff value from 0.5 to 0.2. Let's go and look at the random forest. Confusion matrix. So the sensitivity is 78, specificity 57. The The accuracy is 65%, sensitivity 78%, specificity 57%. So sensitivity is 78% here and accuracy is 65. It's actually not that much better than a decision tree. That's relatively surprising. That is relatively surprising. Oh well, I wonder if I've set this too high. So I'm going to rerun this. This was testing mtry in 4, 8, and 10 using 500 trees. Okay, let's just try increasing this a little bit. Let's go 10, 15, and I'll just use 300 trees. I'm surprised because a random forest is almost always better than using a single tree. 6482. These look to be the exact same. Okay. I'm just going to keep moving. Just look at the variable importance. It shows that the parent's education is the most important. Next by go out and if they have support. It's nice when you created a feature, you engineer a feature, like I engineered parent education and support, and then those show up as being the most important. That's an indicator that your new feature is adding to the model. It's improving the model. The variable importance is a measure of how predictive each feature is. This is based on the mean increase in accuracy, and I believe it's accuracy. I know that there are two different ways. There's information gain and there's the Gini index. I think it's information gain averaged over all of the trees. The most predictive features is parent edu, which is a feature that I engineered, go out, and support, which is another feature that I engineered. Okay, I want to keep moving. Model 3, GOM. Because we are modeling a probability of passing, we need to use the binomial family with a logit link function. I don't have time to filter out any significant variables. Just run a model on the full dataset using all of the variables. Why is this running a model on the full dataset and not using the training data? It's just, is this a trap? I believe that this is a trap. A generalized linear model relates the response to a linear, relates the mean of the response to a linear combination of the features through a link function. This allows for the effects of multiple variables to be taken into consideration at once. The response is binary, and so a binomial response distribution is appropriate. I use a logit link function, which is the most common link function for binary outcomes and ensures that the response will always be between 0 and 1. The default code was set up to use the full data. I wanted to be able to compare the performance with the random forest and D-tree, and so trained the GLM on the training data and evaluated it on the test data. And you can see the formula here is saying pass follows all variables except G3, but I've already removed G3, so I don't need that. And I changed the data to train. I don't need to change this link function. And this is saying predict new data. I want new data to be test. And the cutoff is 0.5, but I really want this to be, well, I'll just keep it as here so that it's the default. And then here's predicted, and predicted final is based on DF pass, but this needs to be based on the test data. So many of the variables are not showing up as being significant. And this should be saying new data is equal to test. Okay, accuracy is 71%, which is higher. Sensitivity 50%, which is lower. Specificity 81%, which is higher. Sensitivity is lower, specificity is higher. And sensitivity was 78% on the decision tree. Here's 58%, but this is using the default cutoff value. So if I decrease the cutoff. Let's look again, the confusion matrix. Okay, sensitivity is 14%. Specificity is 93%. Okay, so this is an interesting result. So the first remark is that a lot of the variables are not statistically significant. And that's what they say here. Wow, there's not a lot of statistical significance. GLM. The model using all of the variables had a high accuracy, but not a lot of statistical significance for the variables, as the p-values were large. Confusion matrix was, where's the confusion matrix? The sensitivity was low at 50%. So I should get rid of the, well, this is just a GLM. Do they have us do any type of variable selection like step AIC or lasso? Okay. So they just say use the results from the tree in order to inform your choice of variables in the GLM work. So I'm just going to include this, and then I'll just go back and look at my random forest variable importance and decision tree. Final GLM is going to be, oops. So I want to go back up to my variable importance, and then only use the ones, I'll just use like the top 5 predictors. Parent, edu, go out, support, FAMS, what does this say? FAMS, support, FAMREL, FAMSUP, FAMREL, health, L, cohol. And let's see, and these have significance. Let's also create some interactions. If you look at the decision tree, you can actually tell where the interactions are, because this is asking, is parent edu greater than 5? Do they go out, right? Do they have health alcohol? So these are related to each other, which means that they're interacting. So we can add interactions between parent, edu, go out, and health. Well, go out and health alcohol. What were the other variables? Parent, edu, go out, support, yes. So let's try FAMSUP fam relation. And oh, many of these do not show as significant. So let's just get rid of a few, and actually let's be smarter. Let's use step AIC. And I have to load the library mass, because that's the library that has the step AIC function. And this results in parent edu, go out, family support, family relation, health, alcohol. So I'll call this, I'll just create a new chunk. And then I'm just using the formula from the step AIC. And then let's look at this one. Okay, so these are significant except for go out. So go out shows us significant in the random forest. It's the second most predictive. However, it's not showing up here. That's probably because I'm missing an interaction effect somewhere. Now let's just go back and think what would be an interaction between going out. If a student was spending a lot of time going out, it could be because they're not studying when they should be, or that they just have a lot of free time. Maybe they're working, maybe they live really close to the school, or maybe they don't have a lot of courses, or maybe maybe they're still studying a lot, but they're also going out a lot, right? So let's add an interaction between study time and go out and see if that improves the significance. So go out times study time. Go out study time. No, it's still about the same. Well, what is study time? Maybe we should just create an indicator. Study time. Let's just say study time is greater than 2. Study time greater than 2. No, this still isn't working. If I don't add it as an interaction, what if I just add it by itself? Okay, so this indicates that I should get rid of go out. And again, sort of the goal here is to be able to write an executive summary that includes a lot of variables that are useful. So right now, if I was writing an executive summary, I would be able to write about education, family support, family relationship, alcohol, and going out. But let's say I wanted to be able to write about more things, then I would need to include more things in the model. So let's just think for a minute. How can we get a model that's statistically significant that includes a lot of variables? Well, we can try changing the step AIC algorithm. So K is equal to multiple degrees of freedom. So K is equal to 2 gives a genuine AIC. K equals log n is sometimes referred to BIC. So what if we just did K is equal to 1? Now we get pass, parent edu, go out, family support, family relation, health, alcohol. Parent edu, go out, family support relation. Okay, let's try using this model. And go out, still not significant. Family relation is now not significant. But we do have interaction between health, alcohol, parent edu, go out, and family support. So you could probably go 2 routes here. You could go the route of, I want a model that is completely statistically significant and all the p-values are significant. And that will probably result in fewer variables. I'm going to use a model that has more variables and say that, but then use it to interpret. So take, for example, parent edu and go out, like the p-value is 0.06, right? So depending on what your threshold is, if it's 0.05 or 0.01 or 0.001, you could say that it's significant or not. In this context, the goal is just to help teachers identify which features could be indicative of a student failing. So if we have more variables, it's actually better for the business context because it provides more interpretation. So I'm going to use this model. So I just have to document this. I tried several GLMs. I started with all variables included, which was above. Many were not significant. I used the variable importance from the random forest to select the most important features, which were parent, edu, go out, support, fam relation, health, alcohol. Then I used the decision tree to find interactions. A decision tree captures interactions because it partitions the data recursively. These were parent, edu, and go out, health, alcohol, and go out, and fam, sup, and fam relation. Many of these were still not, and I should also mention, just as with the random forest, I changed the data so that the model was fit on the training data and then evaluated based on the test data. I also set the cutoff value to 20% from what we decided earlier. So I'm just trying to narrate my process so that when a grader reads it, they can say, oh yes, I see what he did here. This makes sense. And this might change depending on the question on the exam. But in general, if you can just show that you are making steps to improve the model, you're documenting those steps, that should be sufficient. I then used step AIC. Then used stepwise selection to remove variables which were which had a high AIC value. I used both forward and backward directions. I also created a new feature which captured when a student had low study time, and this showed as being significant. While all of these p-values are less than 0.05, only 5 variables are included. School Whiz could benefit from having information on more variables, and so I fit another model using a lower penalty term in the step AIC function. The default used k is equal to 2, but I used k is equal to 1, where k is the term that's applied to the number of parameters in the likelihood, in the penalized likelihood, so that a lower value allows for a more complex model. That's this model here. The confusion matrix is the confusion matrix. Matrix based on the test data is below. What does this tell you? It tells you that no people are predicted to be false, to predicted to not fail, which is not useful. Maybe the cutoff value is too high. No. Let's look at the predicted values. So they're spread out between 20 to 1, 0.2 to 1. What if I set this to 0.5? Okay, so this has a sensitivity of 36, And remember, it's sensitivity that we cared about, right? Let's go back to the decision tree. It was 58% in a single decision tree, and now it's 36%. Okay, well let's look at a lower cutoff value. Accuracy is 65. So a lower cutoff value is indicating a lower sensitivity, so maybe a higher, yes, okay. If I have a higher cutoff value, then I get a higher sensitivity. I increased the cutoff value to 0.8 so that the sensitivity is higher. Okay, now what? Now I need to interpret the results. So this is a logistic regression model, and so you can read the signs of the coefficient to determine the change in the probability. This is because although the linear model, the linear term is actually referring to the log of the odds. If the log of the odds is increasing, then the probability is increasing, and vice versa. If the log of the odds is decreasing, the probability is decreasing. So you can get the direction of change by looking at the sign of the coefficients. Logit model is predicting. The Logit's linear predictor is estimating the log of the odds. The sign of the log of the odds is the same as the sign of the probability of passing. I say probability of passing. Are we really predicting the probability of passing? Yes, G3 is greater than 10. Okay, good. We're not predicting the probability of failure. That would have ruined a lot of earlier work. Although the logistics predictor is estimating log of the odds, the sign of the log of the odds is the same as the sign of the probability of passing, and so the direction of change of the coefficients is can be interpreted as either increasing or decreasing the probability. We don't need to take the exponent. Wait, let me rephrase this. Either as the signs will still be the same. Well, what I mean by that is if you take exponent coefficient of GLM, it will just give you the exponent of the coefficient, which is the relativity factor, if you will. So family relation is 1.3, right? Family relation is 0.1. So family relation is positive, right? The sign of this value is positive, and this value is greater than 1, meaning it's just increasing the probability. Family support is less than 1, which means that it's decreasing the probability when you multiply them together. And if you look at family support, you can see that the sign here is negative. Let's do one more example. Okay, parent edu go out. This is a negative sign, and the relativity is less than 1, indicating that when you multiply all of these together, it would decrease the exponent of the linear predictor, whereas here it would just decrease the linear predictor. So you can interpret these coefficient signs without having to take the exponent. We see that the probability of passing is higher for parents with education, with higher education. Let's just say increases as education increases. As parents' education increases, is higher for students who go out, is lower for students who do not have family support, is higher for students who have positive relationships with their families. Is now this health alcohol variable I don't really like because it's not interpretable. And so yes, this is late in the game, so to speak. That doesn't mean that I can't change it. So I'm going to health. I'm going to go back and I'm going to separate this. So I'm going to create a new variable. So I'm going to add health back to the model and separate it out from alcohol consumption. And okay, I have health and alcohol. Okay, so it looks like alcohol isn't actually significant. So I'm just going to get rid of alcohol. And now let's see. Okay, now I can actually interpret the health variable. And let's just see. I have to copy these coefficients back. Let's see, my emphasis is on being able to interpret the result. So if I do nothing else, I want to get 20 points out of 20 points on the executive summary. And I can only do that if I can interpret the model. Okay, so let's just go back. Increases as parents' education increases. Is positive for going out. Is lower for families which have support. Okay, who have family support. So maybe it means that they're not, financially independent. And then is higher for students who have positive family relations. Is lower for students who have health. Wait. Health is current health status. 5 is very good. So why would this be negative? I'm very, very confused. Health is negative. Okay, let's use health less than 2. If they're in poor health status, we're going to use an indicator. Health less than 2. Okay, coefficient's positive. That would mean that patients who have bad health are more likely to pass. That just seems counterintuitive to me. Okay, I won't change it. I'll keep it as it was. Is lower students who have a high health status. Parent EGU and go out. So if the parents go out, so for students with parents that have high education level, they can still fail if they go out too frequently. And if they have family support and good family relationships. So good family relationships can counteract the need or the risk of failure, can counteract the effect of poverty, which is needing support. So essentially, you want to interpret these in a way that's meaningful. So I could say, well, I'll leave them as so for here, and then when I go to the executive summary, I'll try to interpret them in a more non-technical way. And then I probably want to plot the GLM. I just remembered, because this is a logit model, these plots are not meaningful. In every other GLM, other than binary classification or other types of classification, these plots are useful. But here, I don't need to look at them. I should look at the final accuracy, though. The final was 61%, which seems low at first, but this model was able to predict able to detect the students that would fail 86% of the time. Sensitivity is 86%. All right. Finally, we're on to the findings section. So we've gone back and done the first 3 sections. And lastly is to interpret the results of the selected models. Okay, and I'm just confused because I realized that it doesn't tell you how many points each of these is worth, which is odd because usually they do this. So I'm looking back at the template. And this is actually it's an old solution, but I guess they don't tell you how many points each question is worth. So they don't tell you how many points each section is worth. This is the official solution, and yeah, they don't have points on here. I'm not copying this official solution. I'm going off of what I see. But anyways, it's just strange that they don't tell you how many points each section is worth. Okay, so now I want to split my monitor. I want to zoom out a little bit. Whoops. And then just go up to the top and maybe start with the business problem. So I'm going to open up the project statement again. SchoolWhiz has an opportunity to improve the academic well-being of their students using data from prior school years. We can help students to learn more while balancing other lifestyle habits so that they can get good grades and have fun at the same time. This will help both the students' experience as well as to increase the school's reviews and enrollment rates. By using predictive analytics, I looked at how many students were there. I looked at data from 577 students and identified which factors contribute to a failing grade in the third trimester. Based on the inputs, using information available at the beginning of the school year, I can predict which students will fail 86% of the time. Of those students who end up failing at the end of the third trimester, 86 out of 100 of them could have been assisted sooner by using the result of our model. Now I just want to go through and note what those factors were. So I'll go right to the variable importance. I think that's a good place to start. The most important factors behind behind failure are a parent's education level, mother or father, the amount that they socialize, whether or not they have family support, which in this case is family support or school support. If they have positive relations with their family, having health or alcohol problems, being healthy, and now I can go back and look at the signs. Now I want to look at the coefficients. So I want to go to the logistic model. Each of these can be a positive or a negative. Successful students who pass have, I'll say, the effect of these factors is, now how am I saying this? The probability, the likelihood of passing increases. It's always difficult to word these bullet points. Is higher for students who go out and take breaks. is lower for students who do not have family support, is higher for students who have positive relationships, is lower for students who have a high health status, who are healthy, which is counterintuitive to me. But again, it's too late to change this. I'll just say this was questionable. For students with parents that have a high education level. Actually, if this was really an executive summary and I saw a result that was counterintuitive, I would just not include it. For students with parents who have a high education level, they can still fail if they go out too frequently. And good family relationships can counteract the effects of poverty. Okay, now I can also look at the decision tree. We recognize the need for educators to have actionable insights, info that they can use to help students. To this end, we created a simple set of rules to flag students who are in danger of failing. And here's our rules. These are the highest risk students. The rules are students with parents who have at least a college degree and who do not go out frequently have the highest pass rates. Students with parents who have at least a college degree who go out very frequently and who have good health alcohol rating. Okay, I think this is a good summary of the interpretation. The next step is to go through each of the specific tasks. So I just want to try to write as fast as I can and summarize everything that I've done. Actually, let me go back to this product statement and see what they say. Okay, so in this case, they just want you to state your findings and recommendations and interpret the results and discuss additional steps that could be taken to improve the analysis if I had more time. Okay, so I've discussed these results. To improve this analysis, now you just have to go through and talk about any of the mistakes that you had or questions that you had. So we could get more details from SchoolWhiz regarding the students who were in this study. We had a question regarding the age of the students to include, as we noticed that some were older, 20 to 22 years old. Also, all students came from only two schools. By looking at other schools, we can see if the results of this analysis extrapolate. We also could get more info regarding the mothers and fathers' job status, which was most frequently other. To test to make use of these results, we could pass this information on to teachers and let them use it to help those students who are likely to fail and create programs to assist. For instance, if a student has a bad health status, give them access to online tutoring, or if their parents do not have college education, give them access to, I don't know, community college courses so that they can, support their children with homework. So essentially what I'm doing is I'm just trying to read each of these changes and talk about how it could be used. If they don't have positive relationships with their families, or are in troubled living conditions, provide after-school programs and sports so that they can feel included. If they're not going out enough, or feel pressured into, spending too much time partying, provide positive activities. Now I'll just talk about some limitations. This data looked at only 2 schools, and it could be that other schools show different results. Much of the data is private information and may not be available for other students, or they may not consent to share it. The numeric values that are given for things for relations, study relations, free time, health, others are unexact, are imprecise. We only know that a higher value corresponds to more of something, such as more, better health, better, or more time going out, but do not know of the precise meaning of these. Yeah, and that is what I have so far. So this is, I think, a sufficient amount of information to pass. I have here 700 words in the executive summary. So maybe this is a little bit short. So when you go through this, you might have, if you have time left over, you could just keep adding to this. Go back through the report, check all of your work against the project statement, and take a break, because you do have 5 hours and 15 minutes. So you don't need to spend all of that time in the exam room. You could take a few minutes, take a break, and then come back and then do some final review. Oh, I do need to review. So I'll go to review, spelling and grammar. 585 records of students. Okay. It's going to take me a while to go through all of these. Okay. Just going to skip to the end because a lot of these are going to show up as errors in the spell check, but they're not really errors. So I'll just run the spell check on the final section. Review, done. Okay, and that is it.